All right, so this is probably will be our last screencast lesson for the year. And what we're going to look at today is acid-base indicators, how they work, how we can use them in a titration, what kind of information can we gain from a titration, which we are going to find out is to determine the concentration of either an acid or a base. And then on Friday, I'm going to give y'all a virtual titration lab that Flint Scientific has done and let y'all look at some data and do some calculations and have a chance to at least see a titration lab done. When you go to college, your chemistry lab will have lots of titrations in it. So it's good to have some idea about how titrations actually happen, how they work, and what kind of information you can gain from them. So anyway, let's go ahead and get started. So lots of times when we are trying to determine, let's say, the pH of an acid or a base, you maybe have used litmus paper, pH paper, or maybe even some kind of acid-base indicator. And the litmus paper and the pH paper are both types of acid-base indicators. There are a lot of different kinds of acid-base indicators, and we are just going to look at a few of them in this screencast. So acid-base indicators are compounds whose color is sensitive to pH. So this means that the color of the indicator, and the indicator can be a solid, such as a paper, or it can be a liquid, changes as the pH of the solution changes. These acid-base indicators are either a weak acid or a weak base. Now, litmus paper is probably the most familiar to most people of the acid-base indicators. And this litmus paper will tell you if you have an acid or a base, but it's not going to actually tell you the actual pH of that solution or that gas. Now, most litmus paper uses an indicator that is called, let's see if I can get this right, 7-hydroxyphenoxazone. Hopefully I got that one right. And so this is really an interesting little molecule that we have here. And this picture on the right is a picture of this fabulous molecule. Now, what I really want you to focus on is right here, this OH group at this bottom left. So in case you are not familiar with your ball and stick models of molecules, all of the black, this represents your carbons, okay? All of the white, that represents your hydrogens. The reds are going to represent your oxygens. Blue is going to represent nitrogen. And let me go ahead and change that to black so you can actually see it. And I think that is all of the molecules or the atoms that are represented for this molecule. And we can see that in this complex molecule, we do have some double bonds and we also have some single bonds. So this OH group on this bottom left is the important part of this molecule. And let's find out why. So if you take that litmus paper and you dip it in a basic solution, the OH of the base, okay, so not of the 7-hydroxyphenoxazone, but of the actual base, will take the hydrogen, okay, so it's going to take that hydrogen right here off of that fancy molecule, leaving the indicator as an anion. So that means everything else, so let me scroll back up a little bit. That means that everything else that is left, and let's see if I can maybe circle it in a different color. So including that oxygen, okay? So everything else that's left is going to be considered an anion, which is also that's also the conjugate base of the indicator. Now, bases are going to drive this equilibrium to the right, causing there to be more anion indicator in the solution. Now, that anion, that indicator, is blue in color. So this is why the litmus paper turns blue when it touches a basic solution. Otherwise, when you take that litmus paper and you were to dip it in an acidic solution, it stays red, okay? It doesn't change colors because that H plus, because that proton is not removed from our fancy molecule. Now, besides litmus paper, you do have some other pH indicators. These pH indicators often have something that's called a transition interval. And this is the pH range over which an indicator changes color. Now, universal indicator, which is what we see up here at the very top of our chart, universal indicators are made by mixing several different indicators. So we have this fabulous big range of color changes whenever we use an universal indicator. Now, most other indicators have a much smaller range. Here are some of very common indicators, whether it's phenolphthalein, which we will see. Let me see if I can scroll so you can see the pH range. Phenolphthalein is good to use if you're going to have a basic solution. Methyl orange would be better to use if you have an acidic solution. Okay, so besides methyl orange, there's even methyl red, bromothymol blue, phenol red. Okay, so there's a lot of different. So this picture, this graphic that I have here for you doesn't even begin to cover every single type of indicators that's out there. This is just a few of them. Now, pH paper, which is something else that you may be familiar with, is a paper that's been soaked in universal indicator, so it can cover a big long range. So what you see here is some pH paper, and you can see one of the great things about pH paper is it goes from everything from a pH of 0, so extremely acidic, all the way to a pH of 13, extremely basic. Now, besides using pH paper, indicators, litmus paper, you can get really fancy and also really accurate by using a pH meter. So this is going to be your most accurate and really the most expensive way to determine the pH of a solution. It measures the voltage between the electrodes that are placed in the solution. The voltage changes as the hydronium ion concentration changes. So this picture here is just something that I clipped doing a Google search, and you can see just how much a pH meter can run a person. All right, so the whole point of talking about all these different types of indicators was really to get kind of at the meat of this screencast, which is about titrations. So when you're doing a titration, you are mixing something. You have a Erlenmeyer flask that has either an acid or a base, strong acid or weak acid, strong base or weak base. And it's of an unknown concentration. And so that is what you're trying to determine. That is why you do titrations, is to determine the pH, the unknown, and I'm sorry, not the pH. Let me put that back. To determine the concentration of what is in that flask. So acids and bases are always going to react. And if you have a strong acid in a strong base, neutralization is going to occur. So that acid and base is going to form water, and it's going to form a salt. Now that salt will remain as just ions floating around in that solution. You're not going to have any kind of solid precip that forms in these acid-base reactions. So a titration is the controlled addition and measurement of an amount of a solution of known concentration required to react completely with a measured amount of solution of unknown concentration. So in a titration, you have two things. One is going to be a solution, once again, either an acid or a base, where you know the concentration of it. And you are going to put that in your burette. Now I'm going to show you a picture of that in just a moment. In your Erlenmeyer flask, below the burette, is going to be a known amount of a unknown concentration, once again, of either an acid or a base. So if you have a base in your Erlenmeyer flask, you're going to have an acid in your burette. If you have an acid in your Erlenmeyer flask, then you're going to have a base in your burette. So it's important that they are opposites of each other. During the titration, you will reach a point in which the moles of hydroxide are the moles of hydronium. This is known as the equivalence point. So this is a very important term for you to understand. You will hear this term a lot when you're doing titrations, because it's what you're trying to do when you do a titration is to get to this equivalence point. Now, how do you know that you got to the equivalence point? This is where the indicators come in. You want to use an indicator that will change color either at the equivalence point or very, very, very soon after the equivalence point. So the point in a titration at which an indicator changes the color. So the indicator is going to be put into the Erlenmeyer flask. Okay, so the indicator is not put in the burette. It's put into the Erlenmeyer flask. And once you have that color change, and that color change stays there, and you'll see in the videos on Friday what I mean when I say that the color change persists, it stays there. But when you reach that where the color change happens and it stays, we call that the end point. Now, once again, ideally, you would want to have the end point the same as the equivalence point. So in order for all of that to happen, for you to have an endpoint that's either the same as the equivalence point or the endpoint that happens very soon after the equivalence point, you have to know, first of all, are you working with a strong or a weak acid? Are you working with a strong or a weak base with this titration? And then you also have to know your indicators and know what range do they change colors in, okay? Because the information of the strength of the acids or bases that you're working with is going to help you to determine what's the best indicator to use for that acid-base titration. So here is the setup that I was telling you about. What you see here, it's a very, very long glass tube. It does have measurements on it. So in some ways it kind of reminds you of a graduated cylinder. This is called a burette, and the burette is held up by the clamp that's on a ring stand, and our Erlenmeyer flask is underneath. So once again, either the acid or the base that's within the burette is going to be of a known concentration. And you are going to just carefully, this is the valve that can be open and closed to let just a drop at a time of our known concentration in the burette to go into our unknown concentration in that Erlenmeyer flask. So you're going to put a drop in there, you're going to pick up the flask, swirl, 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 then do the same thing. Open up the stopcock or valve, let some more of the known concentration drip into your flask, shut it off, swirl, 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 and see if the color change persists or not. So you'll see in this picture on the left that the color they're showing probably like a phenolphthalein where it has changed colors. Oh, well, it tells you right there it's phenolphthalein. And so what they're showing you here is that they put NaOH, so they put a strong base, sodium hydroxide, in their burette, and they were working with an unknown concentration of sulfuric acid. Notice some of the other things that they're showing you in this picture on the left. They have a graduated cylinder and they have a pipette. That's one way that you can get your solution of the strong base into the burette. The other thing that I have seen is just putting a funnel right here at the top and pouring it in through the funnel. This is very narrow, so it does fill up quickly. So you do need to make sure that as you're pouring your strong base or strong acid into the burette that you do it very slowly so as to not spill and overfill your burette. So remember, the whole point of doing these titrations is to determine the concentration of the unknown solution in that Erlenmeyer flask. You can determine the concentration of the acid or base in the flask as long as you know the amount of standard solution used. So that is the acid or the base that's in the burette. And you also need to know the concentration of the standard solution. Sometimes the standard solution can also be called the titrant. So let's go ahead and try out a problem. And I want to just make sure I'm giving myself some space here. Okay, so let's try this out. In a titration, we have 27.4 mils of a 0.0154 molarity of barium hydroxide, and it is added to a 20.0 mil sample of hydrochloric solution. The hydrochloric solution is of unknown concentration, and we're going to continue to add that barium hydroxide until the equivalence point is reached. And once again, don't forget, how do we know when the equivalence point is reached? When we see the indicator change colors in there, and as soon as that indicator the color remains, even after it's swirled, the color still remains, that's when we know we've reached the equivalence point or just gone a little bit past the equivalence point. So the question, the unknown, is what is the molarity of the acid solution? So as always, I want to start off by writing out our knowns and our unknowns for this. All right, so some of our knowns. We have 27.4 milliliters of barium hydroxide. And we also know that the concentration of our barium hydroxide is 0.0154 molarity. Now, we've also been told that we have 20.0 milliliters of hydrochloric. And what is it that we're solving for? What is all this information for? Our end goal is to determine the concentration, the molarity of the hydrochloric acid. Now, let's look at these for a second here. Barium hydroxide, would that be a strong or weak base? Hopefully you answered that that would be a strong base. And then let's ask the same question here for the hydrochloric. Would that be a strong or weak acid? Hopefully you would answer that that would be a strong acid. Remember, y'all, it is so important that you know your strong acids and your strong bases, and any acid or base that's not on that list is going to be considered weak. All right, so whenever you have something like this, and lots of times when you're doing titrations, your volume measurements are going to be in mils, you need to go ahead and convert those into liters. So milliliters to liters means moving the decimal 3 times to the left. So that is going to be 0.0274 liters of barium hydroxide. And let's do that for the hydrochloric as well. So that's going to be 0.0200 liters of hydrochloric. Now, besides converting those mils into liters, something else that you really should do is to go ahead and write out this reaction. So what we have here, once again, I'll do it in a different color. We have barium hydroxide plus hydrochloric. Now, because we are dealing with a strong acid in a strong base, notice that I am only writing an arrow that shows the reaction going to completion. I'm not using an equilibrium arrow. And our products for this, so don't forget, barium will go with the chlorine, and the hydrogen will go with the hydroxide. All right, so we're going to make barium chloride. And even though I'm writing this as a compound, the reality is, ladies, this barium chloride is going to remain as separate ions, just floating around in, yep, you guessed it, in water. Okay, that hydrogen plus that hydroxide is going to give us water. Now, once again, this is kind of back to Chem 1 material. Besides having to write the formulas correctly, we also have to balance this equation. So you're going to end up with a coefficient of 2 in front of the hydrochloric and a coefficient of 2 in front of the water. All right, and I'm going to go ahead and put some more space. And so that we can go ahead and work this problem out. All right, so the first thing we're going to do is find our moles of that barium hydroxide. And once again, we're going to use our molarity formula, which is molarity equals moles over liters. Hopefully at this point you feel very comfortable with the molarity formula and all the different ways that you can use it. This is one of those formulas that I feel like we have used a lot this year. So to find the moles of barium hydroxide, that's going to be molarity times liters equals our moles. Let's put our numbers in. That is 0.0154. And our liters is 0.0274 liters. And that will equal our moles of barium hydroxide. So you're going to punch and crunch that, and you should come up with 4.22 times 10 to the negative fourth moles of barium hydroxide. Okay, so now you might be asking, what do you do with this? Well, now we're going to do mole to mole stoichiometry. Okay, so once again, I think I need still just a little bit more space. So here, I'll do it in a different color. Let's take this 4.22 times 10 to the fourth, and we're going to use that at the beginning of our railroad tracks, and we're going to go from moles of barium hydroxide to moles of the hydrochloric. All right, so let's do it. 4.22 times 10 to the negative fourth moles of barium hydroxide. And what's going to go next is our mole ratio, okay, that we're going to get from our problem. Okay, we have an understood 1 right there. All right, so we're going to put that understood 1 mole of barium hydroxide. And we're going to put in our 2 moles of hydrochloric. And once again, we're going to do a little bit of punch and crunch, and you should come up with 8.44 times 10 to the negative fourth moles of hydrochloric. Now, we are not done yet. We still have a little bit more to go because remember the whole point of this was what? To determine the concentration of hydrochloric. So now that we know moles of hydrochloric and we know a volume of hydrochloric, we can go back, use the molarity formula to determine the actual use the molarity formula in its intended way. We don't have to manipulate it at all. And we can find the concentration of hydrochloric. So molarity, moles over liter. And we're going to put in here 8.44 times 10 to the negative fourth moles over, remember, don't forget that milliliter to liter conversion we did at the very beginning of this problem, and that gave us 2.00 times 10 to the negative second liters. Once again, you're going to put that into your calculator and you should get 4.22 times 10 to the negative second molarity of hydrochloric. All right, so that is the whole setup right there. So let's kind of go back at the beginning. We took all the information out of our word problem and we wrote it down. Then we converted our milliliters to liters. After that, we wrote a balanced equation. Then we took our concentration of that titrant, of that standard solution that was put into the burette, and we used that to determine the moles. Then we set up a very simple mole stoichiometry problem where we went from moles of what was in the burette to moles of our unknown in the Erlenmeyer flask. We took that mole amount and with also the given information to us, which was the volume that was in the Erlenmeyer flask, and we could use that information to actually determine the concentration of the hydrochloric acid. Now, if for some reason you are still not feeling super comfortable with what I did, please feel free to watch this video that I have linked in your notes. Also, this would be a great time for you to stop the screencast and go to your textbook, your TRO book, And the problems for this are actually found in Chapter 5 of TRO. And if you look on page 205, you will work problems 57 and 58. Both of those are determining the concentration of an unknown acid or base. All right, just a little bit left. And what other thing I would like you to learn about is titration graphs, what they look like. Now, because you have different combinations, like what's in your burette, it could be a strong base, and it can be mixing, it could be being added to a strong acid. So that would be one kind of graph. Now let's take that and let's flip it. Let's put the strong acid in the burette and the strong base in the Erlenmeyer flask. That graph would look just a little bit different. It would look flipped. It would be like a mirror image. Now, you could also have a strong base in your burette, and you could be adding that to a weak acid. That titration graph is going to look a little different. Or you could have a strong acid in your burette and you could be adding it to a weak base. Once again, yet another graph that looks just a little bit different. So what I want you to do is to go to this Khan Academy website and read and sketch the different types of titration graphs that can be obtained depending upon the strength of the acid or base that's in the burette versus the strong or weak acid or base that's in the Erlenmeyer flask. Now, if you are doing all of this in OneNote, you can go to the top of OneNote under View, go to Rule Lines, and you can pick graph paper in case you find it easier to draw your graphs on there. Don't forget to also denote where the equivalence point would be for each one of these types of graphs. Now, I also have a link to a Bozeman, Mr. Anderson, with Bozeman Science. He gets into the titration graphs a little bit more towards the end of this video. I want to say it's around minute 7 that he'll start looking and showing you the titration graphs in case you would like to use his material instead. Now, what I am requiring you to understand is looking and understanding a strong acid, strong base titration graph. All right, ladies, I think, yep, it is. That is it. That's all of our notes that we are going to be taking on titrations. On Friday, I have a virtual lab for y'all, and so that you can kind of see how a titration is actually done. Y'all have a wonderful day.